Here we can see the problem. We were tasked with creating a prototype of a drug-eluting stent measuring 5 centimeters long and 1 centimeter in diameter that's coated in a drug to prevent clotting. We are asked to calculate the mass transfer coefficient, mass transfer rate, and the mixed concentration of the drug as it exits the stent. We are given a velocity of 10 centimeters per second, surface concentration of 100 milligrams per liter, a diffusion coefficient of 5 to the 10 minus 6 centimeters squared per second, and a viscosity of 1.2, and a blood density as shown. I started by calculating my mass transfer coefficient using the formulas for Sherwood's number and Reynolds number and the Schmidt number, ultimately getting a Kc of 0.001294 centimeters per second. Next, I needed to identify the mass transfer rate J. This was done by using the diffusive flux equation, where C low was determined to be 0, as there was no blood in the system originally. Here I ended with a J of 0.0001294 milligrams per centimeter squared seconds. Finally, I needed to identify C mixed as the blood exits the stent. Here I used the equation for the mixed concentration from our equation sheet. C mix is equal to 2 km L over RV times C high. Solving, I got a mixed concentration of 0.2588 milligrams per liter. Now, on to the experiment. I modeled my experiment using a clear plastic tube as my blood vessel, a wrapper from a roll of dimes I use as bus fare as my stent, some turmeric strategically hidden within the stent to model my drug coating, and finally, water as my blood. As for the experiment itself, we can see our blood is about to flow into the stent. As it flows into the stent, we can see it pick up the coating. Finally, we are left with the C mix at the bottom of the bowl.